This is example 3b of Z transform. In particular, we are again asked to find Yn both for the steady state and the transient response. We're given a difference equation and the xn is a cosine of 0.03 pi n, a very slowly changing cosine with a difference equation. Again, to find the Z transform, to find the output, we again perform Z transform on Yn to get Y of Z, and 0.95 Yn minus 1 becomes 0.95 Z minus 1 YZ, and Xn becomes Xz. Again, we move the YZs on the left hand side and YZ on the right hand side in preparation to get the transfer function. Once we have the transfer function expressed in this form, again we can change it to positive powers of Z or negative powers of Z. For positive powers of Z, it is Z over Z minus 0.95. In this example, as opposed to the last, we are going to play with positive powers of Z so that you can see that we can deal with this problem either on a negative power or positive power. Once I have h of Z, I'm prepared now to get my xn to get into my xn into my Z domain. This is simply a lookup table. So you look up, you get this. And now we can use the convolution in time is multiplication in frequency. So we simply substitute this is h of Z and this is x of Z. So y of Z is equals to h of Z, x of Z, and once we can figure this out, we are going to get y of n. Of course, there are two steps. One is to open up this and by partial fraction expansion, and then finally look up, and then we will get y of n in the few parts. One is the transient part and one is the steady state part. So this is what we are going to do. Alright, so it is non-trivial to do partial fraction expansion because here we are operating with a very complicated expression here. The other thing to take note is that because we are playing with positive powers of Z, the trick is to express the left hand side as YZ over Z first. So notice that this Z came from here originally. It was Z over Z minus 0.5. You'll realize that when we do it this way, just before we do inverse Laplace transform, this Z will go back up again to find YZ. But when we are finding partial fraction expansion, we want one of the Z's to go to the left hand side. So this is actually Xz over Z, and this is Hz. Alright, now you can use the MATLAB's residual to break this equation down into partial fraction expansion. So the take home message is this: I'm using residual because my system of coefficient is in positive powers of Z. In the last example, when your system of coefficient is in negative, then you must use residual Z. Here we are going to use residual. So here please use MATLAB's residual to convert this expression into the partial fraction expansion that I've shown you below. So go and try it by yourself to see whether you can jump from this step to this step using the residual. Let us examine each of these. Just before we are going to convert, we are going to move the Z from the left hand side to the right hand side. So there is a Z here, there's a Z here, and there's a Z here, and now you can use the lookup table. you have a constant minus 3.959 times 0.95 to the power of n. So this is the simple lookup table for the single pole. Now this is a complex conjugate pair pole. So what you have to do is you realize the complex conjugate pair pole will be converted into a cosine. In addition, we have to put up a lot of numbers here, so now I'm going to highlight these numbers for you. The first idea is to convert your rectangle representation into polar notation. So this simply is the polar representation of the guy on top, and the guy below is also the rectangle representation. So convert rectangle to polar, and then we'll use the numbers in this polar. Let's see these four numbers. So I color these four numbers, the numerator's magnitude and numerator's phase. In the bottom I color the denominator's magnitude and the denominator's phase. These four numbers are useful. So where are they? The magnitude becomes the magnitude of the numerator is here in front of the cosine. There is a multiply by 2 because two of these poles, this complex conjugate pole, will join up to have 2 times the magnitude. Will be the final magnitude of this cosine. So that means the input cosine was 1 cosine 0.03 pi n. It has now become 2 times 4.782. So it has become much larger. It went up by close to about 9 times, 2 times 4.7 times. What about this red one? This red is a phase delay. It will introduce a phase delay. Here delay because it's minus. So notice that I am using the positive pole locations phase value, because if you look at the negative J 0.094, you will have a conjugate version of this phase. So to not make a mistake, I always choose the positive real and positive imaginary pole position to look at these four values. So in summary, the amplitude is 4.782 multiplied by 2. The cosine is delayed by this value here, minus 1.0257. Now let's continue. What about this 0.0942? What is this? This is actually 0.03 pi. So when we send a cosine of 0.03 pi, it will exist again. So the phase at the denominator is exactly the cosine's frequency. Okay, and now about 1 here. Well, it is not used because this 1 here is actually going to be the guy in front. It is 1 to the power of n, and since 1 to the power of n is always the same 1, so we didn't put it there. But in the past, if we don't have a 1, if it's bigger or smaller, you realize that the cosine can be growing or decaying depending on this magnitude. Now, so if I ask you which is the steady state, you realize that this is the steady state, because when I input a cosine, I will get a cosine. The amplitude is changed with the phase is changed as well. However, what about this guy? This is a transient, because when n goes to infinity, this guy goes to 0 as n tends to infinity. So this is the steady state response and this is the transient response. So this example shows us the problem of finding the steady state and transient response from a simple difference equation to find yn. Thank you.